So Tor is broken at an infrastructure level. Princeton researchers published a mathematical proof that BGP routing attacks can de-anonymize millions of users, and they call their attack RAPTOR, which means routing attacks on privacy in Tor. RAPTOR isn't a single attack, but it's a collection of BGP-based, specifically designed to break Tor anonymity. Now, let me explain exactly how this actually works and why it matters. BGP stands for Border Gateway Protocol, and it's a routing system that basically directs all internet traffic between networks. Think of it as a traffic control system for the entire internet, basically. When you send data anywhere online, BGP decides which path it takes through thousands of interconnected networks to reach its actual destination. BGP was designed in the 1980s when the internet was tiny and everyone trusted each other, basically. And it has basically zero built-in security. Anyone can announce that they own any IP address range and other networks accept these announcements without verification. And it's kind of like letting anyone put up road signs that redirect the highway traffic to their house. So here's how this fundamental flaw basically destroys Tor's anonymity. When you launch Tor, you connect to what you think is a guard relay in Germany, let's say. But an attacker has just announced fake BGP routes claiming they own that German server's IP address, and your internet service provider believes the fake announcement. Your traffic gets redirected to the attacker's servers instead of the real Tor relay that exists. The attacker sees your real IP address before forwarding your traffic to the actual Tor relay. Your anonymity dies instantly with that. So this is kind of the core Raptor attack method, and researchers identified it with multiple variations. So hijack attacks redirect your traffic permanently to attacker servers. Interception attacks redirect your traffic, but then forward it to the real destination. So you don't actually notice anything's actually wrong. And more specific, prefix attacks announce longer IP address ranges to override legitimate routes. Equally, specific prefix attacks announce the exact same IP range as the legitimate owner. All these techniques exploit BGP's fundamental lack of any kind of authentication or security. The researchers measured exactly how vulnerable every Tor relay is to these attacks, and they used real internet topology data and Tor consensus information from January of 2016. The Tor consensus is a document that's basically published every hour that lists all the active Tor relays, their capabilities, and their bandwidth. Tor clients download this consensus to know which relays are actually available for building circuits, and the results are pretty devastating. Now, they found 1,185 autonomous systems host Tor relays. An autonomous system is a network controlled by one organization, like an internet service provider, for example, or hosting company. Each autonomous system gets assigned a unique number called ASN. For example, Comcast is AS7922 and Google is AS15169. When you connect to the internet, your traffic travels through multiple autonomous systems to reach its actual destination. Many of these networks have pretty terrible resilience against BGP hijacking. Take OVH, for example, a massive French hosting company that runs 339 Tor relays. Their resilience score is only 0.408 on a scale where 1.0 means perfection. When someone attacks OVH's routing, nearly 60% of its users connecting to OVH relays get their real IP addresses actually exposed. Now, Online SAS is another major hosting provider. They score even worse at 0.4 resilience despite hosting high bandwidth relays that many users actually connect to. Now, these aren't small companies. They are major infrastructure providers hosting thousands of popular Tor relays. The researchers calculated resilience for two different attack types: hijack attacks, which again redirect your traffic to attacker-controlled servers, and inception attacks do the same thing, but they also forward your traffic to the actual real destination, so you don't actually notice anything wrong. Both attacks expose your real identity. So for hijack attacks, about 20% of networks hosting Tor relays have resilience scores below 0.32. And that means over 2/3 of users connecting to those networks get compromised when attacks happen. Another 20% of networks have high resilience above 0.61, meaning most users stay protected. Interception attacks show better overall resilience because they're harder to actually execute in the long run. However, the same vulnerable networks still perform poorly. OVH only achieves 0.5 resilience against interception compared to the average of 0.8 across all the networks. Now, the vulnerability varies dramatically by user location. OVH has resilience above 0.8 for 20% of client locations, but below 0.3 for another 20% of clients. So your geographical location determines how vulnerable you actually are to these attacks. Now, why do some networks have such poor resilience? And it really comes down to internet topology, right? Like, think of the internet as a hierarchy. Tier 1 networks like AT&T and Verizon sit at the very top, right? Like, they own the backbone infrastructure and don't pay anyone for internet access. Below them are Tier 2 networks that buy access from Tier 1 networks or Tier 1 providers. Hosting companies usually sit lower in this hierarchy as customers, not really providers. OVH has 4 provider networks that are all Tier 1 internet backbones, and it has many peer networks, but only one customer network. So this topology makes OVH highly dependent on its provider and peers for actual routing. Now, when attackers control those upstream networks, they can easily redirect traffic that's intended for OVH. Networks with more customers and fewer dependencies have better resilience. If you control many downstream networks, those networks will always route correctly to you, even during attacks. However, hosting companies like OVH typically sell services to end users, not other networks, and they end up in vulnerable positions in the internet hierarchy. The current Tor relay selection algorithm makes everything even worse. It chooses relays based purely on bandwidth to give users better performance. Now, high bandwidth relays often run on hosting networks with poor hijack resilience, and users unknowingly select the most vulnerable connection paths. The researchers proved that these attacks work in practice. The Indostat attack in 2014 compromised 44 Tor relays, including 33 guard relays. All 23 affected IP prefixes got hijacked using equally specific attacks. These attacks announced the exact IP prefix length as the legitimate owner, making them harder to detect than more specific prefix attacks. Now, this threat hasn't actually diminished since 2014. For example, in 2023, a BGP hijack targeted AWS infrastructure, which compromised 17 Tor relays, exposing users' real IP addresses for hours before mitigation actually took place. Now, in 2024, suspected deliberate misconfigurations hit Hijacks. Probably mispronounced that, but it's a major Tor relay host, endangering 45% of users connecting to its 287 relays. These incidents show attackers are actively exploiting BGP's flaws, targeting the same vulnerable hosting providers that the Princeton researchers had actually flagged. And I'll have the actual paper pinned as the first comment. Now, Tor's dependence on concentrated infrastructure makes these attacks devastatingly effective. BGP attacks requires minimal resources compared to other Tor attacks. You don't need to break any encryption or exploit browser vulnerabilities or run honeypot relays. You just need to control an internet service provider and announce fake routes. Every government has this capability, essentially. So it is an issue. I'd add to that, so do major corporations and criminal organizations. So keep that in mind. State-sponsored attackers have taken BGP attacks to absolutely new heights. So, for example, in 2024, Cloudflare reported a 300% spike in suspected state-backed attacks targeting Tor, with a Russian ISP hijacking 62 relays to unmask these activists. These attacks used automated tools to inject fake routes in real time, exploiting Tor's public consensus data to pinpoint the high-value relays, where the 2024 Indostat hijack was a kind of blunt instrument. Today's attacks are much more surgical and capable of isolating entire regions. Governments have these capabilities, and they're actively using it to dismantle Tor anonymity. The researchers built 3 countermeasures to defend against RAPTOR attacks, and they've called their defensive system Counter-RAPTOR. First, they created a new guard relay selection algorithm that factors network resilience into relay choice. Instead of just picking relays purely by bandwidth, it actually considers how well protected each relay's network is against things like hijacking. And their algorithm uses a tunable parameter called alpha. Alpha is just a number between 0 and 1 that controls how much weight to actually give security versus things like speed. When alpha equals 0, relay selection works exactly like the current Tor choosing, only the fastest relays. When alpha equals 1, selection prioritizes resilience over bandwidth, choosing only the most secure relays. They recommend alpha equals 0.5 as the kind of optimal balance between security and performance. The algorithm calculates resilience for each relay's network from your specific location. It then combines resilience scores with bandwidth ratings to choose the best relays, preventing users from unknowingly connecting to vulnerable networks. Now, they tested the algorithm using real Tor consensus data and internet topology, and it improved user security by up to 36% on average. For certain locations, the security improved by 166%. The algorithm achieved these gains with very minimal performance loss. The second countermeasure is randomization to prevent fingerprinting attacks. If relay selection depends on your location, adversaries might identify your location by observing which relays you choose over time. The algorithm includes a random sampling to make relay choices kind of less predictable while maintaining the same security benefits that exist. And a third countermeasure is a live BGP monitoring system, and it monitors internet routing in real time and detects suspicious route announcements affecting Tor relays. The system uses 3 detection methods. Origin AS checking compares the announced route origin against known legitimate owners. If someone announces routes for IP addresses that they don't own, the system flags it as suspicious. This method catches all attacks, but generates many false positives also from legitimate route changes. Frequency analytics detect routes announced unusually rarely. Most legitimate routes get announced consistently over time. Attack routes typically appear once or very infrequently. Routes announced below a threshold frequency get flagged as suspicious. Time analytics detect routes announced for unusually short periods. Legitimate routes typically stay active for long periods of time. Attack routes often last minutes or hours before getting checked and removed. Routes active for less than a threshold time end up getting flagged. The researchers deployed their monitoring system in February of 2016 and ran it through May of 2016. They injected simulated attacks based on 9 different real-world hijacking incidents, including Syrian telecommunications, Korean weather services, and multiple wind stream attacks. Their detection system caught all simulated attacks with very low false positive rates. The frequency analytics achieved 0.38% false positives on average. The time analytic achieved 0.19% false positives, and they also performed a real BGP hijack attack using the peering testbed and successfully detected it. Nearly a decade later, Tor's response to these vulnerabilities remains very inadequate, to say the least. The bandwidth-weighted relay selection algorithm is still standard in 2025, guiding users towards vulnerable high-bandwidth relays. Like experimental patches using the researchers' alpha-based algorithms are in testing, but won't be fully deployed until at least 2026. Partial BGP monitoring built with Cadia catches only 68% of simulated attacks, and false positives slow down responses. The Tor project admits that full protection hinges on RPKI adoption, which stagnates at under 40% globally. Meanwhile, users remain exposed to hijacks that can unmask them in seconds they can do nothing about. The monitoring system increases routing transparency for the Tor network. Attackers have to perform hijacks in public view where they can be detected and stopped. However, monitoring only helps after the attacks began, so the protective relay selection provides far better protection. The researchers made their Counter-RAPTOR source code publicly available, so Tor could actually implement these defenses. And nearly a decade later, Tor still has not fully adopted them. BGP's lack of authentication enables routing hijacks against any online service. And we're talking banks, social media, government websites, and corporate networks face the same kind of vulnerabilities. Some internet service providers deploy security extensions like RPKI to cryptographically verify route announcements. However, adaptation still remains really limited and uneven. Most networks still accept routes announced without verification at all. And RPKI stands for Resource Public Key Infrastructure. It's a cryptographic system that enables network owners to digitally sign their route announcements, providing they own those IP addresses. Think of it like a digital certificate that says, yes, I really do own this network. And when RPKI is properly deployed, routers can reject unsigned or incorrectly signed route announcements, which stops hijacks. RPKI was intended to address BGP's trust issues, but in 2025, it remains a partial solution. According to RIPE NCC, only 38% of autonomous systems use RPK, and even then, 15% of those networks fail to filter invalid routes. The RIPE NCC is one of the regional internet registries that coordinates things like IP address allocations in places like Europe. OVH's resilience has fallen to 0.47, but 53% of its users are still exposed during hijacks. Heitzer's fares really no better at the end of the day, with partial RPK leaving upstream vulnerabilities totally unaddressed. Now, attackers don't need to outsmart RPKI. They exploit gaps where it's not enforced. It's pretty straightforward. For Tor users, this means the infrastructure they actually rely on is still kind of a house of cards. And The research demonstrates that Tor's security relies heavily on the reliability of internet infrastructure, which is why it's called the overlay network, which is beyond Tor's control. Granted, most security discussions focus on traffic analysis, malicious code, malicious exit nodes, or browser exploits, but BGP attacks bypass all of these concerns by redirecting traffic before it enters the Tor network. Users can't detect these attacks without specialized tools. Everything appears normal from your perspective. Like your Tor connection works fine. Traffic flows to what looks like the correct relay, only the routing path changes, sending your data through attacker-controlled infrastructure first. Now, individual users can't fix BGP's authentication problems. However, Tor can implement a better relay selection that considers both network security and performance. The researchers provided working code and detailed implementation guidelines. Users are sitting ducks. Tools like BGP Stream or Tor's relay status page are really useless without deep technical know-how, and even then, they don't really warn individuals in real time. BGP Stream is a monitoring service that tracks internet routing changes, but interpreting its data requires network engineering expertise. And the Tor project's 2025 advice, using a VPN before Tor adds costs, latency, and a whole bunch of issues. I'm going to cover Tor and VPNs in another video. And VPNs can be hijacked too. So decentralized relay hosting could reduce resilience on vulnerable providers. However, as of May 2025, only 4% of relays run on community servers. Users are left defenseless against attacks they can't see without any kind of systematic fixes. This vulnerability affects millions of Tor users worldwide. Anyone using Tor for journalism, activism, privacy, darknet markets, all that stuff faces potential exposure through infrastructure attacks. The current relay selection algorithm inadvertently guides users towards vulnerable networks optimized for performance rather than security. And the math is really brutal. BGP hijacks continue to strip anonymity directly away from millions of Tor users, with state-backed attacks and concentrated hosting makes the problem worse in 2025. Recent incidents targeting AWS and Hetzner prove the threat is active and not some hypothetical thing. Global BGP incident reports show only 3 route leaks and 0 hijacks in Q1 of 2025, which is down from the average of 3.6 monthly incidents in 2024. But still, this decrease does not eliminate the vulnerability. And Tor's relay selection still prioritizes speed over safety. While patching and monitoring systems do advance, they're years from full deployment, and RPKI's slow adaptation leaves the internet's backbone wide open to manipulation. Tor has to adopt resilience-based relay selection now, and users really have to demand it. It's up to us. I can't do it because they blocked me, but you can. So, because the next hijack is already underway, most likely. We're going to get more into this in a video coming up, but there's been some developments with this, and it's not particularly good. I mean, it is if you're law enforcement or a nation state, but in any case, thank you for watching to the end. Complain to Tor, stop donating to them, and as always, I'll see you in the next video.